Welcome, everyone. For today's prep, we're just going to look at an example of calculating the curl of a vector field, and then we'll see the definition for calculating something called the divergence of a vector field. Now, the curl, we have this formula, as we saw, that we can use to calculate it, but it's going to be easier to remember this as a cross product. So we have our vector field F with component functions P, Q, and R. So this is a vector field on R3. And we have this del operator. This is our vector derivative operator. And what it does is it says apply the partial derivative with respect to x, apply the partial derivative with respect to y, and apply the partial derivative of with respect to z for each of those components. And so we can think of the curl of f as the cross product of this operator with the vector field. So when we write this as a 3x3 determinant, we can write our usual ijk for the cross product across the top row. Then we put our operators into the second row there, and then the components of vector field f go in the third row. So let's actually see how we use this in an example. So we're going to calculate the curl of this vector field. And again, let's set up our cross product here. So we'll write this as a 3x3 determinant. We have I, J, K along the top row. And then we put our partial derivatives, so partial x, partial y, and partial z in the middle row. And then we list our components of our vector field. So we look for the I component, that's xz, so that goes in the first spot there. Then we find our j entry, and that is xyz, so that's going to go here. And then finally, our k entry is negative y squared, so that'll be our last part of the row there. All right, so now we want to calculate this determinant. And so to start off, we want the I component. So we eliminate the first column and the first row, and what we do is we look at the determinant of this 2x2 matrix. All right, so the way we do this smaller determinant is we multiply down the main diagonal first. So when we do that, now this technically is a multiplication. What we're doing is we're applying the y partial derivative to that negative y squared. So we have negative y squared, and then we're going to apply our y partial derivative. Then we multiply down the other diagonal. Now, in this case, it's not actually, we're not multiplying. What we're doing is we're applying the z partial derivative to this other part, and we subtract. So we have our xyz, and then we're applying the z partial derivative to that. All right, so that's the first component of our cross product. Now, comma, we go on to the second component. The second component of our cross product is always negative, so we'll kind of start that off. And now for the second component, this is the j. This is j. So again, we get rid of the first row and then that middle column. And that tells us what 2x2 determinant we're going to do. So it's formed from these two columns. Multiply down the main diagonal. But again, what we're doing, not really multiplication, what we're doing is we're applying the x partial to this negative y squared. So we have our negative y squared, and then we apply the x partial. And then we multiply down the other diagonal. Again, we're not really multiplying, we're applying the z partial. So we get xz, and then we're applying the z partial to that. And as usual, we subtract. So we multiply down the main diagonal, and then we multiply down the other diagonal, and then we subtract. But because we're doing the kind of the middle component here, there's this extra negative in front. Okay, so that's the first coordinate, the second spot. Now we're ready for our third part here. And when we do this, we want to think about, we want the k location now. So we get rid of the first and that last column, and that tells us which 2x2 determinant we're looking at. And when we do this, main diagonal first. So we're applying the We have our x, y, z, and we're applying the x partial derivative to that. And then we multiply down the other diagonal, so xz, and we're applying our y partial derivative to that. And then we subtract. And that is our curl. Now let's finish doing the partial derivatives. In case you didn't see it, we have our x, y, z. We're doing our x partial for that. And then we multiply the other way, and we're applying our y partial to the xz, and then we're subtracting there. All right, so now let's finish it up. So when we do this, we end up with negative 2y minus xy. So y partial of this is negative 2y. Z partial of this is xy, and we're subtracting. Then we go to the next term over here. The x partial of this negative y squared is just going to be 0. And then if we distribute the negative, this is just going to become positive. And the z partial of xz is just x. And then finally, we do our last component here, and we do our x partial. That gives us yz. And then if we do the y partial of this, there aren't any y's, so that's just 0. And here we go. This is a vector. So when we calculate the curl of a vector field, we get a brand new vector field out. So just a note here. It's a vector. So when we calculate the curl of a vector field like we have here, we've done it, well, we end up with a vector field out. So this gives us a brand new vector. All right, and that's it. That's how we calculate curl. Now we're going to see some interpretations of this a little bit later. But for right now, I just want to kind of get into how do we calculate this? How do we actually calculate it? How calculate this thing? Well, related to curls, kind of along the same lines, is this gadget. And the next one we're going to be looking at is the divergence of a vector field. So the definition for divergence is we have this vector field F. And again, we're considering vector field F defined on a vector field in R3. So F here is a vector field in R3, so three-dimensional space, and it has components functions P, Q, and R, just like our definition for curl. So our vector field here has components P, Q, and R. And the way we calculate the divergence of this vector field, we call this div of function f, and we take the first component, do the partial with respect to x, take the second component function, do the partial with respect to y, and then take the third component of our vector field, do the partial of that with respect to z, and then we just add up the results. And again, this might feel kind of similar, and the reason why is because this might look to you like a dot product. When we're adding up a bunch of terms here, you might think of this as the dot product of a couple vectors, and that's precisely what we're doing here. So a way to think of divergence is, well, you can just remember the formula, or you can think of this as the dot product between that del operator, that vector derivative operator, and our vector field F. So to write this out, that operator, we just saw it with curl, same one as with curl. It's the x partial, the y partial, and then the z partial. And then we do the dot product with our vector field. So our vector field F had components P, Q, and R. And when we do the dot product, we just kind of multiply across and then just add up the results. And that's where this formula is coming from. Now, technically, we're not actually multiplying. We're not multiplying this with p. What we're doing is we're applying the partial derivative with respect to x to that first component. And then we're applying the partial derivative with respect to y to that second component function. So this is mostly a kind of a notational way to remember the formula for divergence, and similar to what we did with curl. Now, the difference here between curl and divergence is, make a quick note of this. The curl of a vector field gives us a brand new vector field on R3. So we actually end up with a brand new vector when we calculate the curl of F. What the divergence does of a vector field is this is not a vector. This is a scalar. So it gives us a scalar field on R3. So with curl, we end up with a vector. With divergence, we end up with a number, a scalar number. All right, so let's see an example of how to calculate this thing. So same vector field that we looked at in the curl example. Now let's just do the divergence. So when we do this, we're going to calculate the divergence of our vector field F. And again, the way to remember this, it's going to be a dot product. So we put our x partial in the first spot, our y partial in the second spot, and our z partial in the third spot. And we're just doing the dot product with the components of our vector field. So xz in the first spot, that's our xz. And then the second component function is xyz. That's from our j component piece there. And then for k, the component is negative y squared, so that's going to go last. And then with divergence, we're just going to take the partial derivative, match it up, and apply that to each of these terms. So in this case, we're going to apply our x partial derivative to the xz component function. And then we're going to apply the y partial derivative to our xyz component function. And then we're going to apply the z partial to that last component function, so the negative y squared. And we're applying our z partial to that. And then when we do this, we add up the results, and that's the dot product. All right, so now let's finish differentiating. So partial derivative of xz is with respect to x is just z. Partial derivative of xyz with respect to y is xz. And then the partial derivative of negative y squared with respect to z is 0. And, you know, we don't normally write 0. So we end up with z plus xz. And so the thing to note again is the divergence of this vector field is we're taking in this case, there's 3 inputs, x, y, and z. And the formula here is that this is z plus xz. And when we do this calculation, the result is this is just a number. So we end up with one real number as the output. So it takes in 3 inputs, x, y, and z. So it takes in a kind of a physical location in 3-dimensional space. And what it gives out is one real number output here. So 3 inputs to 1 output. And the output here is just a real number. So divergence, again, we're just seeing how to calculate this thing. We'll look at some interpretations later on. But the divergence of a vector field ends up giving us a scalar, whereas the curl of a vector field gives us a, well, brand new vector field. Gives us a vector. All right. So next time in class, we're going to see how these two things are. There's a relationship between divergence and curl that we'll look at. And then we're going to start looking see how we can use, in particular, curl here to help us investigate conservative vector fields. All right, so we'll see that in class next time. Bye-bye.